How's it going? In this one, we're going to cover the Kuhn-Tucker conditions for maximization and minimization with constraints, and we're going to go over the envelope theorem. These ones, if you have to study one thing, I would say study these guys because a lot of the stuff that we're coming up on are going to use these extensively, so if you can learn how to apply these, you'll be in a better spot. So, to motivate this, suppose we're trying to solve max or min. It'll be one of the two. I'll just write it as max, but I will say they're going to be the same exact thing as if it was min. So, I'll write it out in vector notation, and then I'm going to go ahead and show you what it would look like in component notation with each of the things written out. So this is the type of problem we are concerned with. So we're choosing a vector of x's that maximizes this function of x's subject to this constraint holding on the x's. So for example, it might be something like max x1, x2 of x1 squared x2 to the third, subject to, say, x1 plus x2 squared less than or equal to 10. Something like that. That's what one of these problems might look like. So in that case, there were two x's in our vector, and there was only one constraint. Sometimes we deal with cases where there are multiple constraints, and in those cases, we use a vector as our constraint. So we'll define x as x1, x2, all the way to xn. Then we'll define g as g1 of x, the vector, g2 of x, the vector, all the way to gm, not nm, of x, the vector. So this guy is a vector of multivariable functions. So each of these components, each of the m components, is its own function of x, the vector. And so similarly, we say b is going to be the vector b1, b2, all the way up to bm. And it makes sense because in this inequality, we're going to have that each component here is less than or equal to the corresponding component of b. So that's why these have the same number of components. So that's how it looks in component notation, is like this. And this is our general maximization problem. Like I said, this could also be min. And sometimes you'll see this inequality going the other way in the way you're treating it. Generally, you're going to want it to match up, so if you have your constraints written out, you're going to want to flip this inequality, i.e. multiply by a negative or something to get them all going the same way. So once they're all the same way, that's how we treat them, is like this. So we're going to now go into the Kuhn-Tucker conditions. The Kuhn-Tucker first-order conditions, which essentially, again, are necessary conditions, but they aren't going to guarantee an optimum. To give kind of a simplified example, suppose I have this function of one variable, and I'm trying to find a maximum. These are the points where the derivative is going to be 0, but obviously only one of them is actually the maximum. These ones are what we call candidates for the maximum, but then we check and see that only one actually is a maximum. So that's this idea of it being a necessary condition, something that needs to be true to be at a maximum, but that by itself isn't enough to guarantee it's a maximum. Unless you're concave, which is another thing we've talked about. So the Kuhn-Tucker first order conditions. First, I'm going to give them as they appear on your reference sheet in vector formulation, and then we'll talk about them in components like we just did. So the conditions are as follows. We're going to have the gradient, the x gradient, I'll break down what this means in a second, sorry. The x gradient of the Lagrangian equal to 0. The lambda gradient of the Lagrangian greater than or equal to 0, lambda, the vector, greater than or equal to 0, and lambda dotted with the lambda gradient equal to 0. And I'm going to be more careful here because all of these should be at the optimum. These are the conditions for an optimum, so these are how we write it. So let's break down what this means. So the x gradient is going to be the vector of all the partial derivatives with respect to x. Oh yes, and I realized I haven't in this video gone over how to set up a Lagrangian, so let's do that quickly. So if we have this formatting from before, the Lagrangian we're going to set up is going to be L of x. It's going to have the entire vector of x's, and it's going to have a vector of lambdas. And it's going to be equal to f evaluated at x plus lambda dotted with the b minus g vector. Again, if we write this out in components, this one's going to be f of x1 all the way to xn. And then this dot product is going to be lambda 1 times b1 minus g1 of x, the vector x, plus lambda 2, b2 minus g2 of the vector x, all the way for your m constraints. And that's how you set up this Lagrangian. This is going to be the same if it's a max or a min problem, and whichever way this inequality goes. So that's how you set up the Lagrangian. Sorry, now let's get back to the FOCs. So the x gradient of the Lagrangian, the partial derivative with respect to each x, is going to be 0. So what that means is the partial of the Lagrangian, I'll write it out this way. There we go. The partial derivative of the Lagrangian evaluated at the optimum with respect to each xi will be equal to 0 for all of the i's between 1 and n. And I guess technically this guy should be the 0 vector. So the next condition, the gradient, the lambda gradient of L is going to be greater than or equal to 0. But the gradient here is going to tell us the partial derivative at the optimum of L with respect to each lambda, and I'll use j for this, is going to be greater than or equal to 0. And here as well it should be vector. My bad. It's going to be, this partial derivative is going to be greater than or equal to 0, but this partial derivative itself is just going to be equal to the constraint when moved to one side. Because here, lambda 1 only enters right here, so this Lagrangian's derivative is just going to be b1 minus g1 evaluated at x. And that has to be greater than or equal to 0, so b1 has to be greater than or equal to g1 of x, which is just the constraint holding. Now this is where it deviates. This is if your inequality goes this way, so g of x is less than or equal to b. If the inequality goes the other way, all of this is going to stay the same except this. This guy's going to flip. That's the only thing. And that just comes from the fact that now b is going to be less than the g. So this is what will flip. And I'll put a little circle around this guy. Flips with this guy. So now then, we see this one just means that for each of these j's, lambda sub j is going to be greater than or equal to 0. I'll separate up here so we can see that all these are using j between 1 and m. And finally, what this dot product means is that the sum of all of the lambda j plus this gradient j is going to be equal to 0, which ends up meaning that for each of these j, there we go, for each of these j, lambda j times b sub j minus g sub j at x has to be equal to 0. We can also write that like this, or b sub j equals d sub j. This guy is just another way of writing this one. So essentially, each of these constraints either has to hold with equality or the lambda has to be 0. And the intuition comes from lambda can be thought of as how you benefit when you relax your constraint, and so obviously one of these two has to be 0. And we've gone over that intuition a little bit before, but generally they're geometric pictures, but I'll skip it for the sake of brevity in this. Yeah, this is what you really need, is how to apply these Kuhn-Tucker first order conditions. So what you do is after you've written all these out, you proceed with the algebra and see where it leads you. And you're going to usually end up with 1, 0, or multiple possible first order condition satisfying points. Then you check which one of these is actually the optimum you're looking for, and you circle it. So a very common way of solving these is by breaking into cases. So if you have a couple of constraints, you could say, okay, what has to be true if lambda 1 is positive? Now what has to be true if lambda 2 is positive? What has to be true if this guy is positive? And break it into cases in that way, see where each algebra leads you, and then get your results. And we'll go over some examples in later videos, but these are the conditions. So the last thing I want to cover in this kind of math breakdown video is the envelope theorem. So we'll define v as a function of theta as the solution to a maximization, again, or a minimization, but I'll write it as a maximization problem, of the max of f of the vector x. And I'll include the parameters. So what this is saying is here we're maximizing this function with no constraints. We get to choose the x's, we don't get to choose lambda. Here lambda might be prices, it might be w's, it could be anything that is a parameter that we don't get to control. For example, what if I'm doing x1, x2 of ax1 plus bx2 squared? Or I guess minus bx2 squared, something like this. A and b we don't get to control, so they're in our theta. We would say these two are parameters. We use theta to represent parameters. Why math is so obsessed with using things multiple times, I don't know, but this has nothing to do with angles, this has to do with being a parameter. So the envelope theorem tells us that the gradient of v with respect to theta is going to just be equal to the partial derivative of f with respect to the thetas evaluated at the optimum. And this is again the annoying vector way to write things, but if you instead write it as each component, what you get is that the partial derivative of v, I'll circle and point to this, the partial derivative of v evaluated at theta, essentially the solution to the maximization problem given some parameters theta, the partial derivative of that with respect to one of the thetas, theta I we'll say, is just equal to the partial derivative of f, I'll leave that off, partial derivative of f with respect to that theta evaluated at whatever your optimum is. Evaluated at your optimum x and plugging in your thetas that you have. And so you would solve this optimization problem normally, taking theta as some given number. Then you would figure out what x star is going to be. And then to find this derivative, you just plug that x star back in. And one of the things that allows us to see is how our value changes. For example, if this is to be thought of as a utility situation, and these thetas are prices, we can see how much our utility changes as the prices change. And that becomes rather useful in later things. And there is a homework problem on one of the homeworks that deals with hotellings, or otelling, I don't know how to pronounce it, and Shepard's lemmas. I might make a video about them, I might not, but this is the envelope theorem. So that's kind of the end of the two-part math overview. I highly encourage you guys to read over his midterm kind of cheat sheet. There is some stuff on there that I didn't cover, but I've covered what I think are the most important things. Notably, also, there is concavity and tangent planes, and also supermodularity. Those are kind of more basic level things that I haven't covered. For concavity, second derivative is negative, that kind of idea. Tangent plane, there's a formula for it, so that's why I didn't cover it. If you need it, it'll be on that cheat sheet. And also, super and submodularity, he went over it in class, and I don't anticipate it being on the exam very heavily. I may be wrong on that, hope I'm not. If you would appreciate if I go over it, shoot me an email or something. But yeah, so I've covered what I think are the most important things, what I would have covered if we had the in-person session. Hopefully this was in some way useful. Now we can get into applying this math.